Hey, welcome. Think about this for a second. All around you, right now, there's an entire invisible universe of signals. They're carrying music, our phone calls, our favorite TV shows, and they're doing it silently, through what seems like nothing at all. So how in the world does the invisible become audible? How does empty space become a superhighway for information? Let's dive in.
It really does feel like magic, right? How does information just leap from a radio tower to your car, or from a satellite orbiting the Earth all the way down to your phone, with literally nothing connecting them? Well, the answer isn't magic, but it is just as amazing. It all comes down to one of the most incredible discoveries in the history of physics, the electromagnetic wave. All right, so to get to the bottom of this, we've got to go back, way back, to the 19th century, to a brilliant physicist named James Clerk Maxwell. He was staring down a major puzzle. See, the laws of electricity and magnetism were pretty well understood, but Maxwell found a specific situation where those laws just fell apart.
So it all kicked off with a pretty simple setup, something like this: a basic circuit with a battery and a capacitor, which is really just two metal plates with a small gap between them. Now, as the capacitor started to charge up, a current flowed through the wire, just like you'd expect. Okay, no big deal there. But the real head-scratcher, the part that didn't make sense, was that empty space, that gap between the plates.
You see, back then there was this core rule in physics, Ampere's law, that said a flowing electric current always creates a magnetic field around it. And sure enough, in the wire, it worked perfectly. But in the gap between the capacitor plates, there's no wire, so there's no current. The law said there should be no magnetic field. And yet, when they actually measured it, there was a magnetic field there. It was like finding a footprint where no one could have possibly walked. Physics was broken.
And this is where Maxwell comes in with this absolutely brilliant idea. He suggested that as that electric field was building up in the gap, the change in the field was acting like a kind of invisible current. He called it a displacement current. It wasn't made of moving charges, no, but the changing field itself was creating the magnetism. Just like that, with this one elegant idea, the law was fixed. But what Maxwell did was so much more than patch a hole. He kicked open a door to a whole new universe.
But fixing that law, that wasn't even the main event. That was just the beginning. Maxwell realized that this deep connection, this interplay between changing electric and magnetic fields, wasn't just some weird quirk of a capacitor. It was a fundamental property of how the universe works. And this is what it all led to, the concept of an electromagnetic wave. So get this. A changing electric field creates a magnetic field. But what happens when you have a changing magnetic field? Well, it creates an electric field. It's this incredible cycle. They create each other, kind of leapfrogging through space, one spawning the next. They don't need anything else to keep going.
And here's what it looks like. In this wave, you have the electric field oscillating, say, up and down, and the magnetic field oscillating side to side. And the really crucial part is that they're both at right angles to the direction the wave is actually moving. It's this beautiful, self-sustaining dance that can just zip through the total vacuum of space, forever. Okay, now this is the part that must have just blown Maxwell's mind. He took his new unified equations for electricity and magnetism, and he used them to calculate the speed of this new theoretical wave he just dreamed up. And the number he got was this: 3 times 10 to the 8th meters per second. 300 million meters per second.
Now that number probably sounds familiar, right? It wasn't just some random speed. It was, with breathtaking accuracy, the known speed of light. The conclusion was just unavoidable. This wave, born from pure math about electricity and magnetism, traveled at the exact same speed as the light coming from the sun. They had to be the same thing. Light is an electromagnetic wave.
Can you imagine that realization? It completely flipped our understanding of reality on its head. It meant that the colors we see with our eyes, the visible light, that wasn't the whole story. It was just one tiny piece of a much, much larger, totally invisible reality. An entire spectrum of these waves had to exist. And this is what that new reality looks like, the electromagnetic spectrum. Just look at that tiny little sliver in the middle. That's everything we've ever seen with our own eyes. All the rainbows, all the art, all the sunsets. But all around it, stretching out in every direction, are these other waves, all with different frequencies and energies that are every bit as real.
So if we look at the high-energy end of the spectrum, you've got the real heavy hitters. Gamma rays let us peer into the very heart of an atom and are used in medicine. X-rays, as we all know, let us see right inside our own bodies. And UV rays, the same ones that give you a sunburn, can be harnessed to sterilize surgical equipment.
Then you go to the other side, the lower energy waves, and these are the absolute workhorses of our modern life. Infrared is the wave of heat, used in everything from night vision cameras to physical therapy. Microwaves, well, they're not just for popcorn, they're crucial for radar and telecommunications. And then you have radio waves, the very backbone of almost all of our wireless communication.
Okay, so let's bring this all the way back to our first question. How do we actually get a song from a recording studio into your car? Well, the answer is we've gotten really good at making these invisible radio waves do the carrying for us.
So here's the challenge, right? The actual sound waves from music or someone's voice have a really low frequency, and on their own, they just don't have the juice to travel very far at all. So we need a way to give them a piggyback ride, basically.
And that piggyback ride has a name. It's called modulation. It's actually a really clever trick where we take our low-frequency information, the audio signal, and we stamp its pattern onto a much more powerful high-frequency radio wave that we call a carrier wave.
So what does that actually look like? Well, we start with our audio wave, and we generate a powerful high-frequency carrier wave. Then we use the audio to change or modulate that carrier. Now, there are two main ways to do this. We can change the carrier's amplitude, its height, to match the shape of the audio wave. That's what your AM, or amplitude modulation radio, is decoding. Or we can change the carrier's frequency, making the waves bunch up and spread out to match the audio. And yep, that's FM, or frequency modulation.
But of course, these waves aren't just zipping through empty space. They have to travel through our atmosphere. And it turns out our planet has this incredibly complex relationship with the electromagnetic spectrum, acting like a giant filter, a shield, and an amplifier that makes life as we know it possible.
Way up there, we have the ionosphere, which is this layer of charged particles that's absolutely perfect for bouncing certain radio waves back down to Earth. That's what allows for long-distance, over-the-horizon communication. And a little closer to home, the ozone layer does us this incredible service by soaking up most of the sun's most dangerous high-energy UV radiation.
And it's not just about blocking things out. The atmosphere also manages infrared waves, which, well, that's just heat. Radiation from the sun warms up the Earth, which then radiates that heat back out as infrared waves. Gases in the atmosphere trap some of that outgoing heat, which keeps our planet at a livable temperature. And that, of course, is the famous greenhouse effect, and it's all about how our planet interacts with these waves.
So think about it. It all started with a tiny crack in a 19th century physics law, and from that, we discovered this entire hidden reality that's all around us all the time. We learned how to see with radio waves, how to diagnose with X-rays, and how to build our entire modern world on these invisible signals, which really makes you wonder, right? If this entire, vast universe of waves was completely invisible to us just a short time ago, what else might be hiding in plain sight, just waiting for us to figure out how to see?